You already have the camera and game loop. Now we will grow a complete grass field, one deliberate step at a time. The finished field repeats one segmented blade as exactly 24,000 instances. Along each blade, normalized runs from 0 at the root to 1 at the tip. This shared coordinate lets later effects target corresponding regions consistently across the entire meadow. Next, build one reusable blade before thinking about the whole field. The first two lines normalize each row into T-watt and taper its half-width. The next pair converts T into height and a gentle squared rest curve. Then, the text chord stores height, giving the vertex shader the same normalized coordinate. Finally, upload mesh transfers the completed arrays to GPU buffers only once. More rows produce smoother bending, while too few reveal visible facets. Keep the mesh narrow and double-sided, because grass must remain visible from either direction. The field now contains 24,000 blade transforms distributed across a 6.0 unit area. Each blade keeps a stable position, while random yaw and size prevent obvious repetition. Because every instance reuses one uploaded mesh, the geometry does not need duplication. Next, connect those matrices to the shader's instance transform attribute. getShaderLocationAttrib tells raylib where each per-blade matrix enters the shader. Scatter field then prepares exactly 24,000 persistent transforms before rendering begins. Inside the loop, getTime updates only the small time uniform. Begin Mode 3D activates the camera you already have in your project. DrawMeshInstanced submits the blade, material, matrix data, and instance count together. The CPU does not issue 24,000 separate DrawModel calls. Instead, the vertex shader bends every copied vertex in parallel on the GPU. Then, fix the subtle mistake that makes ordinary wind look rubbery. A naive tip at dx, L has length square root dx squared plus L squared. That distance always exceeds L whenever the sideways push is non-zero. Instead, constrain the tip to a circle of radius L around its root. Pythagoras gives y as square root L squared minus dx squared. The table shows fixed height falling while the true radius remains 1. Meanwhile, naive length climbs from 1 to 1.41 at full sideways reach. Clamp the radicand to 0 before square, preventing negative inputs and NaN vertices. First, normalized TOT scales blade height into rest length S, measuring each vertex from the root. World position and phase offset gust and flutter. Weights 0.6, 0.22, and 0.18 scale their blend by wind strength. Then TT squared concentrates DZ near the tip, while the clamped square root preserves length S. Finally, instance transform places the corrected vertex, and MVP converts it into clip space for rendering. Phase and tint come from world position, so variation stays stable as phases travel and roots remain planted. Add rows for smoother bends, disable backface culling, and preserve one DrawMeshInstanced call. Finally, color the corrected geometry instead of hiding structural problems with shading. The first mix moves from a deep root color toward the lush middle. The second, smooth step, introduces the warm tip color across the upper half. Next, the wrapped dot product remaps lighting from -1 to 1 into 0 to 1. Diffuse, therefore, stays between 0.55 and 1, keeping shaded faces readable. The last line combines a warm key with a smaller cool sky fill. Add stable tint jitter before this lighting, when you need hand-painted variation. The finished rule remains precise. Lighting adds mood, but fixed length comes from bending on a circle. You now have one uploaded blade, 24,000 stable instances, layered GPU wind, and soft golden hour shading. Remember the governing rule: bend on a circle, never by adding reach.